Let's get started with this subject matter of today. And it's about this thing we call spin. What the hell is spin? A quantum property, they say. Well, it started about, 1922. Have these two fellows, okay? And they created a little experiment, okay? Remember, this is when the atom was being concocted. You had Niels Bohr and you had Rutherford. They came up with this planetary atom, and so some people started playing with the electrons, meaning electricity, meaning current. Okay, and so these two fellows, German guys, they set up this magnetic setup where they had these magnets going through two magnets, and you can see they're lined up and pointing in all different directions. That's what they expected under what is known as classical mechanics. Okay, and when they tried it with electrons, there's current. They only got two versions, the ups and the downs. Okay, so you can see the difference between the classical, if we can call that we'll call it classical mechanics, where the magnets, where the tiny magnets are shot through these two magnets. They're pointing up. They're pointing in the direction in which they were moved by the two big magnets. Okay. On the other hand, when they ran a current, it was black or white. It was up or down, or just two directions. And from that, they concocted that there was something called spin. And you say, what do you mean spin? Yeah, because see, when you have a charged particle that moves, it creates, or it takes with it, I guess you could call it. I don't know how quantum mechanics really visualizes this, because they talk about it, but they never really visualize it. They never can really make an image of what they're talking about. And so you have this charged particle. It moves and it carries with it its so-called magnetic field. So if you have this electron, it's a charged particle, right? It's going to move, creates this magnetic field, and what they're saying is this magnetic field, because of these two magnets, can only have two directions. One is up down. Well, it's up down in both cases, but in one case you get the downs, and the others you get the ups, and that's what they found in the lab. Okay, so the first problem I'm going to point out here in what Gerlach and Stern did is the notion that quantum mechanics has. The irrational notion that quantum mechanics has of what electricity is. These people think, even to this day, that electricity is the flow of electron beads. Okay, and so if each bead carries with it this magnetic field, that's this halo that surrounds it, which has never been well defined, because when you go look for the word field, it's just a bunch of numbers that surround an object. Okay, electric field, magnetic field, gravitational field. Just a bunch of numbers. Somehow those become physical objects when they're giving a physical interpretation. But what's the problem? The problem is the notion of electricity that quantum mechanics has, and that the entire establishment has, and it is passed down from generation to generation, and nobody ever questions it. Okay, and here it is. Okay, you have the classical mechanics, which believes it's a flow of electron beads from, going from valence band to valence band, from one atom to another. Okay. It's really not the classical in a sense that classical mechanics never really had this kind of atom. But I'm sure if we bring James Maxwell back to life and we said, look, the electron is a little bead and orbiting the atom, this is what he would come up with. He would say, well, yeah, then electricity is the flow of electron beads from atom to atom. What quantum did was get rid of the atom. They got rid of the atom altogether. They don't use atoms anymore. They just flow electron beads. So when they talk about electricity going from cathode to anode, they talk about electron beads, little balls going from one to the other, as if you have nothing in between. In fact, if you evacuate the chamber, allegedly, you would think that more beads would flow because the mean free path has increased. And I'm going to talk a little bit about that later on, because someone asked a question about that, and I'm going to address that at the end of the lecture today. Okay, what's our model? Well, you can't do electricity without physical objects. Okay, you need a physical object. What's the physical object? Well, in the case of a chamber where you evacuate everything, you still have atoms and molecules in there. Okay, and what happens, these molecules, and you have quite a few of them, by the way, hundreds of thousands per centimeter cube, by the way. But you have these molecules, and they're bound to each other. They're merged. Their electron shells under the Roche model are merged, and they spin in situ. And it is that spinning in situ, it's the torsion of that whole, what we call serpentine, that is what we call electricity. Okay, so we have a different model, in other words, of what electricity is. Okay, so let me get back in here. So we start off on the wrong foot, because what happens is quantum mechanics believes not only that electricity is the flow of beads, but when you go even one step back and say, okay, what does your atom look like? They have the planetary atom. That's the only way they can explain the electricity. That's the only way they can explain ionization. That's the only way they can explain quantum jump. They have this little bead going back and forth, and somehow it goes from energy level to energy level, whatever that is, right? Orbitals, whatever those are. Okay? And when it does so, it releases energy, meaning a light. Okay? And what is that? That's the planetary atom. And the only question that any mechanic of quantum has to answer, very simple. Why doesn't the electron bead fall, negative especially, to the positive nucleus, proton? Why doesn't it fly away spontaneously? What keeps it rolling around in a circle? And if they can't answer that question, we're going to take the microphone away from them. They're not allowed to give their presentation. Because if they cannot answer what keeps their model, they cannot present a model that's rational, that's saying, well, this is the electron bead and it goes back and forth, or it flies out when it does electricity, or when it does ionization. Tell me what keeps it bound to the proton to begin with. Why does it fly away spontaneously? Why doesn't it fall to the nucleus? You need to put a physical object between the electron bead or the proton, otherwise you're doing black magic. And that's what quantum mechanics does. Black magic. They have no physical interpretation for any of their subatomic phenomena or mechanisms. And that's why Mr. Bohr, all the way to Mr. Feynman, they said no one understands quantum mechanics. Of course they're not going to understand it, because they don't have a valid model. The discrete model of particles is bunk. 150% of it. None of it survives. Okay, you can't explain the invisible world of Mother Nature's with your planetary model of the atom or anything below that. Okay, it's all math. None of it is physical interpretation. Okay. So what is this spin thingy, this property, this behavior, okay, this weird one? Well, if someone asked you to spin a top, I guess you would do what you see there. You grab the top with a couple of fingers and just twirl it, okay? There it is. That's what spin is. You look up the definitions. Those come from the Wikipedia, but you'll find the same ones everywhere. Essentially, it's not a terribly scientific word. Okay, spin, a rotation or circular motion of an object around an internal axis. What is rotation? Circular movement of an object around a center or point of rotation. Simple, straightforward, we're done, right? I mean, someone says, is the top spinning? That's the notion you're going to run through your mind. That's what you're going to think, okay? And not these people. These people, they have a different notion of spin, especially when it comes to quantum mechanics. But here's the issue. The issue is, the problem is that spin, traditional spin, classical spin, was handled by the mathematicians. That's where the problem is. Mathematicians is an individual who has no notion whatsoever of physics. Okay? And what they do is they try to apply math to something that requires no math. Math can only describe, and that's what the mathematicians do. They cannot explain. Okay? And that's where the problem is. They have no physical interpretations of anything today, because all they do is describe mathematically. And in this case, they created a concept known as angular momentum. Okay, you have linear momentum, something just goes straight, and angular momentum goes around. Straightforward. Okay, so they created angular momentum, but there's two types of angular momentum. Okay, you have the spin or angular momentum. You have the orbital angular momentum. Okay, so let's look at those. Let me get rid of this one here. Here it is. This is a notion of or the notion they have of what. Oh, I got to reverse. Let me get it. Now that's better. This is what is known as spin angular momentum. Okay, what is it? You look at the surface. Think of a point on the surface, for example, and it's going to rotate with respect to the center. Okay, so you're looking at the surface of a single object. Okay, we're talking about only one object here, and you're going to look at one point on the surface. It's going to rotate with respect to the center. Straightforward. Okay. But here we have the orbital one in comparison, so that you can see what the difference is. Orbital means that it's more like the Earth going around the sun, or the moon going around the Earth, or a kid, revolving a ball at the end of a string. Okay, another object revolves or orbits around the center of the first one. Okay, so we have these two notions. One is the surface of one object. The other one is a separate object, and it's just going around some center for whatever reason, a horse around a post or whatever. Okay. Okay, so those were the two notions of angular momentum that these people came up with. Let me clear this a little bit here. Okay, and what's the problem? The problem is that quantum mechanics does not enjoy, the particles of quantum mechanics do not enjoy these extrinsic behaviors. Okay, quantum particles only have intrinsic behaviors, among them angular momentum. Okay, and so this is what they're talking about. Okay, extrinsic property that an object has because of what it's doing. If you're orbiting around something, or you're spinning on your own, on yourself, around your axis, right? Then that's an extrinsic property, because you're comparing the edge against yourself. Okay, but then you have here the intrinsic property. Like you have an intrinsic property, and it's your mass, how much you weigh or whatever. Okay, and this is more or less something similar. Property of an object has because of what it is, and what they're saying is spin, as it applies to quantum particles, is an intrinsic property, not an extrinsic one. Okay, so it's going to be something with which the electron was born. Okay, irrespective of what happens outside its surface. Okay, so that's the notion we have here. Okay, here we have one of the problems that quantum particles have because of that. It says quantum particles have no extrinsic properties that can be pinned down. Quantum particles have no comparable classical behaviors. Okay, so if you were thinking about a particle rotating around itself or something along those lines, or even spinning around, like in the case of the electron spinning around the proton, they say that's not true. Okay, they teach you that in high school, but when you get to the university level, they try to kill that notion completely, especially if you're studying so-called mathematical physics. This follows from the uncertainty principle. What is that? Well, the more precise you can determine a particle's position, the less you know about its momentum. Okay, there you have the little equation that says, change in position times change in momentum. It's got to be less than that value there, which is Planck's constant divided by 2. That came out of Mr. Heisenberg, Werner Heisenberg. Okay, and the other version is the shorter the time window, the less you know about the particle's energy. Okay, and vice versa. In other words, quantum particle is totally unpredictable. And I like to make fun of these people because I think they deserve it, okay, every bit of it. And so here I show him Mr. Heisenberg, and what he says, when the ball will stand still, it doesn't move. That's what his equation is telling you in physical terms. And when the ball moves, it doesn't stand still. No kidding. Okay, so that's what Heisenberg got his Nobel for. I hope you understand. Okay, hope you get the notion here. Okay. Okay, so let me get this back up. This is the problem with quantum mechanics, or at least you could call it a problem. I call it a problem, but you could say, well, this is just a description of what quantum believes in, what quantum has, what they do. Electrons are non-solid objects. We start there. Okay. In fact, usually it's treated like a wave, a field. And they say that's its natural state until you look at it, until you measure it, until you do something with it. Then all that collapses suddenly by magic, okay, to a particle, to a point particle, to a location essentially. Okay, and now you can measure, do whatever you want. As soon as you take the measuring tape away, or the scale, or whatever you're using to measure it, it goes back to occupying the whole universe. Okay, so that's the notion. It's this magical thing that they essentially cannot explain. It's nonsense, total nonsense. It's point-like. It has no internal structure. Okay, what does that mean? Well, how can something spin if it's got no internal structure? You see the problem that they run into. Because if it's point-like, what part is spinning with respect to what? You're not talking about the point on its surface. You're talking about the fact that it doesn't even have body. There's no structure there. Okay, so what are we going to do here? How can you get something to spin that has no body? Okay, and spin is a static concept. Okay, in quantum mechanics, it's essentially orientation. It's a tilt. It's like I like to describe it as you make a mark on your top and you spin it. Okay, and when it stops, if that mark is pointing upwards, well, you call it spin 1. If it's pointing in the opposite direction, pointing downwards, you call it spin -1. It's pointing to the side, maybe you call it spin 3/2 or half or -1 or whatever. You give them numbers. That's what they did. They gave numbers to these static notions, essentially. Okay, because it's when they measure. And at that moment that they measure, they say, well, this one's got a different spin, orientation, tilt, whatever, than that other one. And we're going to call this one half, the other one minus half. Remember, they're mathematicians. They have to put numbers to these things. What number are you going to put the spin? So again, it's that they're using this word spin to really mislead you, because every time they talk about spin, they insinuate and do even more than that. They're to talk about a top. And you say, okay, I know what electron spin is. Yeah, you take a top, you spin it, that's what an electron's doing. And everybody's okay with that, except until when you put them against the ropes and say, okay, hold it, what is spin? Oh no, it's not the same thing as a top. So what was he talking about for the last 2 hours? Talking about spin, for example, they talk about spin, the electron spinning in two different magnets, of why they attract each other, and they tell you, well, it's because the electron spins. What do you mean by that? Even if the two electrons spin, two balls that spin, how does one top attract another top because they're spinning in the same direction? How do they repel if they're spinning in opposite directions? I mean, you got to explain the mechanism, not say, well, it's because they spin. Spin what? What do you mean? It's got half spin, or three halves plus half makes 2, or what do we do here? I mean, what is all that? That doesn't give you a physical interpretation of how a magnet attracts another. But that's how they use it. They use the word spin in that way. They insinuate they're talking about spinning. Okay, so they have these different weird spins. Okay, and what do I mean by that? Well, here you get a difference between, for example, fermions and bosons. The bosons, okay, as I call them. Good name for them. Fermions, electron, muon, neutrinos, they have half spins. Okay, which are half integer multiples of Planck's constant divided by 2 pi, okay? And then you have the bosons, which are the photons, gluons, W's and Z's, the weak forces there, okay? And they have integer spins, okay? And fermions obey Pauli's exclusion principle, okay, which means 2 fermions cannot exist in the same state, whereas bosons can congregate in the same state. Okay, so this is how they separate these, and they give these properties, these mathematical properties, these descriptions to all these particles, okay, and that's their world. What's it got to do with spin? I don't know, beats me, okay, really it doesn't have to do with spinning, like spinning of a top, okay. Okay, so how do they infer these things, okay? You say, I mean, if it's not spinning, it's not spin, then what is it? And how do they come up with all this stuff? Well, quantum spin is like the spin of a planet, okay? In that it gives a particle angular momentum and a tiny magnetic field called a magnetic moment. Okay, so we have this magnetic, this little magnet, because that's what they think an electron is, a little magnet, whatever a magnet is, because they don't even know what a magnet is. Okay, it's got this magnetic field around itself, this halo. Okay, and what happens? However, because of calculated particle sizes, okay, you look at what the diameter or the radius of one of these particles is. Once they calculate it, okay, the surfaces of these charged particles would have to move faster than light, the surface, right, if it were spinning, to produce the measured magnetic moments. Okay, so imagine the top, okay, and it's going to spin. Okay, here I am, one. Okay, imagine the top. You look at the surface here, the edge, okay, and what happens? You think of it spinning, but the smaller you make it, okay, the smaller you make it, the faster the point on the outside, on the surface, is going to go around. When you get to these particles, which are measured or calculated to be very, 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 very small, at some point you exceed the speed of light, of rotation. The little edge, whatever particle you imagine being there, is spinning faster than the speed of light. And that's why they say these particles cannot spin in a classical way, okay? In other words, in a rational way. That's what classical means. Classical means rational, okay? Because in the old days, they were still trying to explain these things in a rational manner. We've forgotten about all that, and when quantum and relativity came along, they started giving irrational physical interpretations. Okay, and here's an example of calculation out there. I'll just briefly go through it. Don't get scared. I'm not going to do any math. Not interested in that. You get the radius of an electron, for example. 10 to the minus 13 centimeters. That's a calculated value. It's an approximate value of what they think the radius is. And you look at the mass, 9 times 10 to the minus 31, okay, kilograms. Okay. And to calculate the radius, there you have the little equation. And you can see there's that little c, which is 300,000 kilometers per second. Okay. What happens? That to get an angular momentum of h bar divided by 2, which is Planck's constant, okay, variation of it, with subluminal rotation speeds, the electron radius must be greater than what? The Compton radius of the electron, which Compton calculated to be 10 to the minus 11 centimeter. Remember, when the exponent is smaller, that particle is bigger. Okay? So if you get to minus 11, minus 10, minus 9, minus 8, the electron is getting bigger, bigger, and bigger. Okay? And they know that the electron can't be that big. It's got to be smaller, smaller, smaller. Well, if you make it smaller, all you're doing is making that little point on the surface of the electron going faster and faster and faster. And at some point, again, you exceed the speed of light. And so they say that's because that's how they figured out that the spin of a subatomic particle, such as an electron, is not the typical spin of classical mechanics, of a top spin. Okay? That's probably the best way to put it. Spinning of a top. Electron doesn't spin like a top. Okay, so here is the conclusion from quantum mechanics, essentially, why the electron cannot spin like a top. Mass would have to rotate faster than light. The mass of the electron. The charge, because remember, charge is a physical entity according to quantum mechanics, not a concept as it is in rational science. Charge would have to also rotate faster than light. That means that whole field, that halo that surrounds the electron, that's got to be spinning also faster than light because of these calculations. And then the ratio of the electron's magnetic moment to its angular momentum is off by a factor of 2. So if they do the calculations, that's what they end up with. They said then it cannot be spinning. Therefore, the electrons don't spin and they don't orbit either. Meaning what? If they don't orbit, it means that they're not orbiting the proton, which is the model that Niels Bohr and Rutherford essentially came up with. So if not doing that, if it's not orbiting, what the hell is this electricity that's flowing, which is the electrons moving from valence band to valence band? So all that falls apart. It falls apart because we have a problem in the model of the atom. They cannot conceptualize their own atom. They don't have any idea today what an electron looks like. They said they've taken pictures of the atom. The Swedish group there that I showed the other day, they filmed the electron. They know everything about it. But then when you put them against the wall, they say, we don't know what it looks like. What do you mean? You took a picture of it, you interviewed it, you had all this stuff, they put them on TV, and then they say, we don't know what it looks like. Great. And what was that I saw on TV, Okay, here are my conclusions on this electron, spin, electron, especially the electron. Remember, it's not the only particle that's alleged to spin. Again, bosons and all fermions, etc., all these also have spin. Okay, well, my conclusions, these are mine. Okay, quantum mechanics, electron is not a particle. Not a particle in the traditional sense of a particle, okay? Corpuscle, grain of sand, a speck of dust, etc. I'm talking about a real particle. It's nothing like that. In fact, it's not a particle at all because allegedly it only becomes a particle or condenses to a pinpoint only when you measure, see it, or touch it, or whatever. As long as you don't look, they say, electron has this mind of its own. As long as you don't look, it's spread out and it's a field. A vibrating field, whatever field is. What is it? A three-dimensional fishnet, like general relativity has its space-time. This net, this canvas. Is that what it is? The vibration of a point in space-time. Is that what it is? A lot of people imagine it that way. Anyways, electron has no body. Okay, so there is no radius. What radius are you going to talk about if you got nothing in front of you? No body means space, empty space. That's what it is. And that's what they're saying the electron is, essentially. Electrons don't orbit the proton, okay, because they don't orbit anything. But if they don't orbit, do they flow from atom to atom? Then we have a problem there as well, because then if they don't orbit, what is this electricity stuff? The flow of electron beads from atom to atom, is that what electricity is? Or is it like I showed under the rope model, a torsion of a bunch of merged electron shells from different atoms and molecules? Okay, so that's probably a better model. Okay, electron doesn't spin on its axis. Okay, so spin is a property the mathematicians invented and misnamed to describe an unexplained mechanism that makes electrons behave as magnets. That's what spin is. It's just something they invented to talk about the magnetic properties of an electron. And they don't know what a magnet is because to this day, no one can tell you in quantum mechanics how a magnet attracts another. They cannot explain, forget about the quantum world, they cannot explain this. How here we have two magnets, okay, and they cannot explain that. Something as simple as that. I mean, how difficult can this be? Let me get this out of here. A second here. I mean, how difficult can this be? Here you have two magnets, okay? We put them together and they stick. There's two objects, two little magnets. There's something in here they call magnetic field, whatever field is, okay? And somehow produces this magic. And to this day, no one can explain this. If they cannot explain this, how are they going to explain something they don't see, such as the magnetic moment of an electron? I mean, they had to start here. You cannot explain this, the attraction, how this attracts that physically, much less are you going to talk about something you cannot see that has the same properties. Okay, so this is what they have to explain. Very simple. And of course, a mathematician has no idea what physics is about. That's why all these mathematical physicists, so-called physicists, all they do is study math. But they have no idea of the physical world. They cannot explain the real world. In other words, they cannot give a physical interpretation to the real world because they're using, great measure, they're using the quantum atom. Okay, and that's the planetary atom. And of course, you cannot explain anything with that atom. And yeah, there's got to be something in here, and that something is a physical object. It's an object that's in there that we cannot touch or see. But as James Maxwell said, and also Mr. Faraday, you know, there's matter in motion. There's some exotic matter in motion that makes up what we call a field. All those lines of force, as Mr. Faraday said, there's something physical in there. And he was right, there is something physical. The threads of the rope. We have threads in there. Each one of those little lines is a thread. It's known as a thread, a physical object that's sweeping around. And all those threads are creating the so-called, that's what we call the magnetic field. And yeah, we can explain with that how attraction and repulsion. You know, if they're hitting against each other, the threads, they push each other away. You have repulsion. You turn one of the magnets around 100 degrees, 180 degrees, and now they're both going in the same direction. And when one comes down, the other one comes up, and now you have attraction. Very simple mechanism, baby stuff, kindergarten stuff, to understand it. Whether you believe it or not is not a question. It doesn't concern science. Okay? And so, yeah, when they get into the spin stuff, they don't know what they're talking about because they're measuring, essentially, what they're doing under the rope model. What you have is a membrane, and that's what the electron is, a membrane. And the membrane is made out of the threads itself. Okay? And those threads are spinning in situ all around, like Mr. de Broglie said, the guy who said that electrons behave as waves as well. And so they're spinning in situ all around the electron shell because they make up the electron shell. They weave the electron shell. And if this one's going around, this one on this side, let's see if we can get it in here. This one, better do it with a ball. Maybe that's the best way to do it. So if this little piece here, this thread here is moving in this direction, guess what this one's moving? Well, it's moving the opposite direction. They have to be in opposite sides, and now we can find out why Pauli's exclusion principle is true, because one side had better be opposite the other side. Okay, Mother Nature doesn't understand half spins and minus spins or zero spins. Mother Nature understands clockwise and counterclockwise, and that's what the thread is doing. One side is clockwise, the other side had better be counterclockwise, and now we have Pauli's exclusion principle there. We need not use this word spin and insinuate that there is a spinning something in there, which is not spin, which is an orientation or a tilt to which they assign a number and with which they cannot give a physical interpretation to absolutely any phenomenon out there.